So now that we're done discussing differential rate laws and integrated rate laws, I want to get into the theory of chemical kinetics. We're going to use several different concepts to develop a model for chemical kinetics. And in this lecture, I want to discuss collision theory, how molecules collide so that bonds get broken in the reactants and new bonds formed to make products. The major idea with collision theory is an intuitively obvious one. Reaction rate, or how fast a reaction goes, is going to be proportional to how many collisions you have, the number of collisions that you have per unit time. So the number of collisions per second, let's just say. Okay, this seems like a reasonable idea. The more collisions you have, the faster your reaction is going to go. However, there are some limitations. If all collisions between molecules resulted in a chemical reaction, then all reactions would occur instantaneously. Let me give you an example. Let's take a reaction where HI decomposes to hydrogen and iodine. Okay, so 2HI goes to H2 plus I2. Let me give you some data for this reaction. When the concentration of HI is 1 times 10 to the minus 3 molar, there are 3.5 times 10 to the 28th collisions per second, okay? And this occurs at a certain temperature. Okay, this data pertains to some temperature. So theoretically, this number of collisions, now don't worry about the math behind this, but theoretically, this number of collisions should result in a rate of 5.8 times 10 to the 4 moles per liter seconds. Okay. However, at that same temperature, the experimentally observed rate is 1.2 times 10 to the minus 8 moles per liter seconds. Now, I want you to compare this experimentally observed rate with the theoretically predicted rate. The actual experimental rate is 12 orders of magnitude, almost 12 orders of magnitude slower than what's predicted from the number of collisions per second. So what this is telling us is that reactions do not occur instantaneously, clearly, and obviously, not all collisions result in a chemical reaction. Okay, so that is the limitation. Obviously, not all collisions produce a reaction. So there must be more than the sheer number of collisions to consider when we think about bonds breaking and forming, because not all collisions can result in a chemical reaction. So, in addition to just the sheer number of collisions, reaction rate depends on some other things as well. Okay, so you have reaction rate depends on mainly three factors when we're talking about collision theory. The first factor is, as we just said, the sheer number of collisions. Okay, that makes sense. The more collisions we have, the faster the reaction should go. But it's not only the number of collisions, it's the quality of those collisions. The reaction rate depends on the number of molecules that collide with the proper orientation to react. So if you want a bond to be broken, you have to have the collision occur in a certain way. The final factor that reaction rate is going to depend on, and this is a very important one, we're going to spend a lot more time talking about this in this lecture and then in subsequent lectures. The reaction rate depends on the number of molecules that have the minimum amount of energy that you need to react. The number of molecules with the minimum amount of energy required to react. This minimum amount of energy required to react has a very special name. It is known as the activation energy. The minimum amount of energy for the molecules to react. So the activation energy, we are going to abbreviate as capital E with a little a subscript. Sometimes the A is uppercase, sometimes it's lowercase. The activation energy has a few specific characteristics. It's always positive, never negative. So it's always positive, always greater than zero. The activation energy depends on the reaction. Okay, it depends on the nature of the reaction. On the nature of the reaction. Every reaction is going to have its own unique activation energy. And one interesting thing about activation energy is that temperature does not affect it. It's independent of temperature. It's independent of the concentration of the reactants that we start out with. Okay, depends on what they are, but not how much of them there are. Okay, so now we need to deepen our discussion of activation energy a little bit. We need to discuss another theory to supplement collision theory, which is transition theory. Okay, so this is not a contradictory theory. It's just kind of deepening our discussion of activation energy. So, in transition theory, we think about the reaction pathway. So, transition theory is to explain or at least contextualize the pathway that the chemical reaction is going to take. So transition theory holds that just as collision theory before it, collisions result in making or breaking bonds. Okay, it's reactants colliding together that is going to make the action happen here. Now, at a certain point in your reaction, molecules will have partially broken bonds. So the reactants will have partially broken bonds on their way to becoming products, and the products have, partially formed bonds. So, this idea of a species that has partially broken or partially formed bonds is called this species is called the activated complex. The activated complex is also sometimes known as the transition state. I usually refer to it as a transition state. They mean the same thing. And sometimes I abbreviate transition state with TS, with this little double cross superscript. So when I label graphs later, you will know what TS means, transition state. So the activated complex is a species with these partially formed or partially broken bonds. And it's interesting energetically because the activated complex occurs at the maximum energy point of a chemical reaction. Now, we can calculate the amount of the activation energy, okay, EA, the activation energy. You can get that amount by taking the difference between the maximum energy and the starting energy of the reactants before the reaction starts. So I'll show you how to do this graphically in the next lecture, but that's just an important kind of concept. Finally, I really want to emphasize here that the activated complexes, this is really just an idea. It's just a concept. Activated complexes can never be isolated. Okay, we don't really actually know that they exist in every reaction, right? It's just an idea to help us understand how long reactions take. Okay. So in the next lecture, I will do an example where we plot the progress of a reaction in terms of energy versus the reaction pathway.